So we have the final USB hard thingy that's really Alright. This is the last, and I think I just want to keep this. But this is the last YubiKey Neo that I have, so see it. The last one here. See more hands up.
Right here. Right here.
Wow.
Damn. That one moves. Just hurt somebody.
Wow, that one fast. Unfortunately, the YubiKey thing is right here. They're really
Correct. Second phone.
Did it just fall out yet?
Yeah. Oh, it'll just continue to throw that at me.
No.
It looks like a giveaway. You caught that knocking, right? Yeah, I got it and I gave it back. Exactly. How foolish.
I gave it
You can tell from mine. I'm an iPhone Yeah, I hate
Great, so the final talk we have here is
right now.
Topic is resource public key infrastructure. So very complex topic, and we have Andrew Gallo, sorry. Andrew Gallo is going to be talking about it. Andrew? Thank you, and thank you for sticking around for the last talk. I always hated the conference talks right before lunch where the guy has a corny joke like I said before we do the conference call. I have the unenvious position of standing between you and free beer. So, luckily for you, I talk fast, hopefully not too fast to get my point across. Research public key infrastructure is a little bit different than many of the talks we've heard today and last night. And it's not about malware or host infection. It's about securing the routing infrastructure on the internet. So be kind to an old routing guy. So I'm more of a network guy than a security guy. I don't have a obligatory about me slide, so that'll have to suffice. So as cliche as it is, the internet really is a network of networks, and it's a bunch of organizations that agree to abide by the same rules. It's self-organizing in that there's no central authority. Currently, on the IPv4 internet, there's around 500,000, 510,000 destinations. And by destinations, I mean networks or prefixes, not individual hosts, obviously. The network could represent anywhere from a handful of hosts, around a couple hundred to several million. So this is a diagram, a relatively recent diagram of the internet, or something that looks very much like it, because the internet has properties of other large-scale long-tail networks. So the question is, how do you find your way through 500,000 routes? How do you know to get from your host to one of the servers or hosts that we just scanned or saw, or trying to hack something? So we use the border gateway protocol. It's the way network operators share information about the topology of the internet. And as you see, the guy in the space-looking suit for protection is the border gateway protocol. This was taken when I was on a mountain biking trip in Colorado, and some space-looking guy kind of landed on Earth and showed us the way to Utah, and that's how we found our way. BGP I classify as a wildly successful protocol. It was first standardized in 1998 with a relatively recent update in 1994. It has not really changed much since then, but still has been flexible enough to carry everything from IPv4, IPv6 with no real extensions, unicast, multicast. It is used both on the internet, in the enterprise. It allows people to pass security information using BGP flow spec. It is a highly configurable and malleable protocol. However, BGP is based on trust, like most of the protocols we grew up with, like Telnet and Clear has been replaced by SSH. HTTP has mostly been replaced by SSL. SMTP has hopefully been mostly replaced with Start TLS, or at least added that so it's not unclear anymore. But BGP still remains a protocol based on trust. There are some mechanisms to protect the protocol itself, such as MD5 hashes, which are passwords on the sessions. Time to live security, which says I'm not going to accept sessions unless they have a specific TTL, as well as access control lists, which control who can talk to my BGP speaker. Again, these only control or protect the control plane itself. When BGP was standardized in the late 80s, the internet wasn't a thing. It was still NSFNet, and it was based on people knowing who you were in order to set up a BGP session. The problem we run into in this situation is there's no ability to determine who is who on the internet. I was going to put in there the classic cartoon of no one knows I'm a dog on the internet. What happens is there's no hierarchical routing or addressing on the internet. Any IP block can exist anywhere on the internet at any time. This is either explicitly or implicitly a reaction to the very centralized, very prescriptive public switch telephone network, which the internet is mostly supplanted at this point. On the one hand, this solved the problem of decoupling location and identity, but it introduced the problem of scaling as well as identity control. Scaling is a whole other topic. Identity control is what we're talking about today. How do I know you are who you claim you are from the perspective of advertising IP blocks? In the old days, as legend has it, John Postal had a spiral-bound notebook and would write down each organization's IP prefix and their assignment, and that's how IP addresses were assigned. This map is a 1987 map of the NSFNet, and it is the only official documentation I have for my organization's assignment way back in the day. I'm sure there's an email from John Postal somewhere. I'm sure it also doesn't exist anymore. The registry that covers the United States, ARIN, has since used the carrot and stick approach to get organizations like mine to register and sign something called a Legacy Resource Agreement so that we no longer need to rely on this map. However, this is how informal IP address assignment was way back when most of the addresses were assigned. So if that's how they were assigned on pen and paper, how are they validated? Well, very seriously, they weren't. BGP, again, is based on a trust model, and there's nothing in the protocol to allow for the validation of identity. There's no relationship between an IP prefix, an autonomous system number, and the organization that's advertising it. The current state of attempting to use this information or to protect yourself from misidentification is to use internet routing registries such as the Routing Assets Database, which is a phenomenal resource. Whois data that's run by any number of organizations. And to collect this data and then put it in a format that can be used to form routing policies. The problem is the IRRs, and there are many of them, don't necessarily have the same information. The data can sometimes be out of date and erroneous. So what happens when things go wrong, when this data is invalid or unreliable? Well, there are any number of hijacking, classic hijacking stories of BGP on the internet. I've highlighted a couple of them here. The Pakistan YouTube hijack is probably the most classic, where the Pakistani government issued a letter to their largest provider and said, we want you to block YouTube. That black hole leaked to the internet and caused massive outages for YouTube. It is still debated whether or not that's a mistake or intentional. That's irrelevant for this conversation. But it shows how easily a small part of the world or a small part of the internet's policy can leak and disrupt the entire internet. An ISP in Brazil leaked the full table. Luckily, this didn't get very far. China Telecom did the same thing. Not the whole table, about 37,000 routes. The most interesting one happened last year, and I'm surprised it's not making more news. Gallo SecureWorks, who is here, I'm not plugging them, I'm just saying they did a great paper on this. a bunch of folks did a BGP hijack on Bitcoin miners that were hosted in AWS and stole some money. It is a phenomenal analysis of both BGP hijacking and Bitcoin mining. And Dell SecureWorks, if you look up Dell SecureWorks BGP hijacking, I'm sure you'll get to that page. This happens primarily because of mistakes. People fat finger something and it propagates farther than it should have. It could be in the case of you want to just clobber somebody's network and black hole them. It could be for fun and profit, as we see in the Bitcoin example. And it could also be the fact that you're trying to direct traffic to you so that you can sniff it and then send it on its way so that most people wouldn't know that you're doing this. That takes a little bit more advanced action because you have to mess with TTLs and is not necessarily something that is seen very often. Real quick, a couple of diagrams on how this works. BGP, there are about 12 different ways to select the path. One of the ones at the top of the list is shortest path. So if you have a network down here, 172.16.00/16, and somebody else claims it, the shortest path wins. So the person up here in the upper right-hand corner, the client, will follow the shortest path to get to you. You have now just stolen that address block. You could set up fake web servers, send out spam, whatever you want to do. More insidious, and this is just how network routing works, more specific prefixes that have longer masks, such as more bits, will win even if it's a longer path. The current state of the art, as I mentioned, is to use whois data, letters of authorization, and have operational staff manually check this, hopefully in a semi-automated fashion at least, to check whois data and create route filters. It doesn't really work that well, as we've seen. There's some BGP monitoring services, such as BGPmon, Cyclops, I think Thousand Eyes does something like this. And if you're the victim of one of these hijacks, your options really are to call your upstream, post to NAV, and depending on the mood of who's monitoring the list at the time, it will depend on how well that will work. Or you can attempt to advertise more specific routes of your own address block, which is what YouTube did in order to get back the addresses from Pakistan. So in comes RPKI. Resource Public Key Infrastructure is a relatively new technology that is meant to provide a cryptographically traceable trust chain from the authority of the IP addresses. It's an extension to 509 that carries IP address block information, and it is called a route origin attestation, sometimes called a route origin authorization, or a ROA. The IANA, run by ICANN, is the source of all addresses, but they don't hold the single root certificate. It was decided that each of the registries, and there are 5 of them in the world, would hold self-signed certs as the root of their resources. 2 modes of operation. There's hosted and there's delegated. And in the hosted environment, the registries all run their own PKI infrastructure. Delegated model is more appropriate for ISPs that need to delegate and sub-delegate address blocks. Row of contents include who my autonomous system is, or who am I, what the IP address block is I'm advertising, and validity dates. So once you've signed your routes and told the world, I am authorized to advertise these blocks, what do you do? Well, that's all you really need to do if you're concerned about protecting your own resources. If you want to check for other people's validity, you now need to go and collect the rows from these things called trust anchor locators, or TALs, which are what the regionals run in order to pass these certificates from the originating party to the relying party. The key here is that there's no cryptographic processing on the router. It's all done by adjunct machines, so that you don't need to worry about processing load on the router. You don't need to worry about that for RPKI. You do need to worry about that for secure inter-domain routing, or CIDR, which is an effort in the IETF working group in order to do path validation. If I didn't make this clear before, RPKI is about origin validation in that you are allowed to originate a specific IP block from a specific autonomous system. This is a block diagram of the setup. There's some crypto engines in the back. They feed to the trust anchor locators, and you as an operator then connect to the TALs, pull down those ROAs via rsync, do some crypto processing, and feed digested information to the routers. I left ARIN, which is the North American regional, in gray. There's an explicit agreement you need to sign in order to, or at least click through in order to get the ROAs. That's a whole other discussion for a day. If you're on NANOG, and you remember about a month or two ago, there was a lot of discussion about that. I apologize, I started that. I should have let John Kern know ahead of time his email box was going to explode. There's basically, ARIN says you need to indemnify us, hold us harmless, and defend us in the event that something goes wrong with the system. Again, another talk, but it does raise some interesting questions about the legality or the legal implications of this system. Routes have 3 states. They're valid, which is good. They're unknown, which is the state of most of the routes today. And they're invalid, which means it's either an invalid origin, an expired certificate, or it's possible that there's a valid ROA for another part of that prefix, such as a summary route, that just doesn't cover the route you're advertising. So what do you do with this data once you have it? Well, right now, nothing. 95% of the route table is unsigned, so you're not going to be making policy decisions. In a fully deployed RPKI environment, what do you do with this information? Do you reject invalid or unknown routes? Do you set local pref low, which says I don't want to use this route? Do you set communities? What do you do? That's still up for operational debate. And this is a key, this is a place where if you want to participate, developing operational best practices are still up in the air. So this is an area where you may want to take a look at. If you're interested in doing this, study RFC 6483. It discusses what the states of the routes are and how they get into those states. There are a lot of good public resources. This is a BGP validator that Wright open sourced. Wright, which is the European registry, is a leader in this space. Although this particular one is hosted by LATNIC, the Latin American and South American regional, which also has the most ROAs in the table. You can go to these and check any prefix on the internet, and it'll tell you if it's unknown, valid, or invalid. There are also some great command line tools. There's 2 routers I have in the resource slide. You can secure shell 2. And there are Junos routers, you can run some commands and see what it looks like from the router's perspective. BGPLON also runs a GUID server that lets you look up the validity state of any prefix you want. So we've solved everything, correct? Well, not really. We've only solved origin validation. The CIDR working group at the IETF is working on path validation. And there's still work to be done with RPKI and again, operational best practices. And the best part is, RPKI, like all new things, introduces some vulnerabilities. These trust anchor locators become valuable targets for both denial of service as well as attempting to own them and provide false data, which is partly ARIN's concern. And there's also the bootstrap problem of how do I trust the path to the trust anchor locators. This is I wonder if it's a Gallo incompleteness problem concerning the internet. A lot of interesting work going on in this space. There's slow adoption. Obviously, the graph shows Wright is the leader in terms of space signed by ROAs. And lastly, if you are not a BGP speaker, it doesn't matter. Your organization uses general internet access, even if somebody else manages it. You should be asking them, when are my routes going to be protected? If you have applications hosted in Amazon, Azure, any other provider, you should be asking them, why aren't my routes protected? The Bitcoin mining attack was done against AWS IP space. Some resource slides if you want to check the web page I showed, as well as go get into a router. I'll post these slides. And here's some contact information. So again, thank you for staying so late and enjoying the rest of the Any questions you can ask me now, or just hit me up on Twitter. So thank you.
This validates that prefixes come from the AS that it's supposed to?
Correct.
What happens if
AS is hijacked to a fundamental way or otherwise establishes a transit leak. This can't, if an entire AS is hijacked, this can't detect it. You still need to rely on the immediate upstream and peers to filter that inappropriate aspect. It doesn't solve everything, but it's a very important step forward.
Because I know they need to divert your traffic down. Or the good ones. Some of them.
See you next year.
All right.